For this video, we are going to solve a situation or problem related to steel connections. Given are the details, figures, and 4 questions which we are going to solve as we go along in this video. To better understand the given situation, let us consider the 3D view of the given figures. Now, we can clearly see that there are middle plates sandwiched by thinner plates at the top and bottom. These plates are held in place by 8 22 mm diameter bolts, thus giving us a butt-type connection. This connection is subjected to a tensile force T. Also, in the problem, we are given the spacings, namely S1, S2, S3, and S4, along with the thickness of these plates. That is, the thickness of the top and bottom plates, T1, and the thickness of the middle plate, T2. For the first question, we are asked to determine the allowable tensile load based on tension on the gross area of the plate. Let us recall the concept or formula stress is equal to force over area, because from this concept came the formula we are going to use to solve this particular question. Ft is your stress, or specifically the tensile stress on the gross area. From the situation, Ft is given as 0.6 of Fy, and also Fy is given as 248 megapascals. T is the force, or specifically the allowable tensile load you are finding for this question. Lastly, Ag is your area, or specifically the gross area. To better visualize the gross area, let us introduce a cutting plane that will cut specifically on this part of our connection. If we'll consider the cut section, it will look something like this. Clearly, we can see 3 plates, but what we must consider is the critical among these 3. If you'll consider the top plate, you also need to consider the bottom plate, because these 2 plates will simultaneously resist the tensile force T. Therefore, the thickness you'll consider should not only be 12 mm but 12 times 2, which will give you 24 mm. Notice that the thickness of the middle plate therefore would be significantly less, being your T2 as 16 mm, compared if you'll choose either the top or bottom plate, which your thickness must be 24 mm. Hence, the middle plate is your critical plate, which now we can see where the gross area is. Having a length of 2S1 and an S2 and a width of T2. Going back to our formula, we now have our Ft being 0.6 of Fy equals T, which is still unknown and what we are looking for in this question, over Ag being simply the formula for the area of a rectangle. That is length times width. Your length being the quantity 2S1 plus S2 times your width being T2. Since Fy is given, we now have 0.6 of 248 equals T over. Let's focus on the first quantity. S1 and S2 are given. S1 is 40. Therefore, 2S1 would be 2 of 40 plus S2 is 80 times T2 is given as 16. In addition, your first quantity is also your gross length, which if you'll calculate would have a value equal to 160 mm. Solving now for T, we now have a value equal to 380,928 newtons, which we must convert to kilonewtons, therefore having a value approximately equal to 380.93 kilonewtons, because from our question, the answer is required in kilonewtons. And this is the final answer for the first question. Let's proceed on the next question, in which we are still asked for the allowable tensile load, but now it is based on tension on the net area of the plate with the following assumption. The same concept will be used for this question, because if you'll notice on the formula we will use for this question, it is somewhat similar to the previous formula we have used for the previous question. Only that the tensile stress now is for the net area, therefore our area would of course be the net area. Hence, the force T would now change. Ft is given as 0.5 of Fu from our situation, and also Fu is given as 400 megapascals. To better understand the net area, let's introduce a cutting plane that will cut our connection specifically at this part, hitting the bolts of the connection. If we will consider the cut section, it will look something like this. Notice that not only the cross-section of the plates are clearly seen, but also the cross-section of the bolts used in our connection. The thickness of the middle plate is still significantly less compared to the thickness of the top and bottom plates. Therefore, our critical plate would still be the middle plate, which we will still consider in solving this question. Now, we can see where the net area is. Net area because it is the area left from the covered area of the holes for the bolts. Going back to our formula, we now have Ft being 0.5 of Fu equals T over the net area, which is the sum of these spacings, S1s and S2, or simply from the previous question, this entire length is your gross length, L. G. Then subtract two hole diameters, which can be determined by using the bolt diameter given and also the following assumption stated in the question. So we have minus 2dH. Then multiply the difference by the thickness of the middle plate, which is simply T2. Since Fu is given, we now have 0.5 of 400 equals T over. Let's focus first on the first quantity. A while ago, we have computed for the value of Lg, or your gross length, which is simply 160 minus 2dH. From the assumption stated at the question, the hole diameter is 3 mm more than the bolt diameter. Hence, we now have the quantity 22 being the bolt diameter plus 3. Then multiplied by T2, which is simply 16. This entire expression at the denominator is simply your AN, or your net area, which if you'll calculate will be exactly 1,760 square mm. From the code provisions, we have what we call the maximum net area, AN max, which is simply 0.85 of the gross area, AG. From the previous question, we can calculate the value of AG to be exactly 2,560. Solving now for AN max would give you a value of exactly 2,176 square mm. Based from the value that we just got for AN max, we can therefore say that AN is safe to use. Hence, we can proceed on our calculations a while ago to now solve for the value of T. Solving now for T, we will have a value equal to 352,000 newtons. Converting that value to kilonewtons would give us a value of exactly 352 kilonewtons. And this is the final answer for the second question. Now, let us consider if the tensile load T acts in such a way that our middle plates would behave like this. Because for the next question, we are asked still for the allowable tensile load, but based now on bolt shear. Therefore, T would cause bolt failure at our connection. Still, the same concept, stress is equal to force over area, will be used for this question because our formula in solving this question would be this. Stress being the shear stress, and from our situation, the allowable bolt shear stress, capital FV, is given as 120 megapascals, which will serve as our shear stress FV in this question. The force would be the shear force V, and the area would be the shear area AV. To better understand the shear area, note that the tensile load T that is seemingly acting on both sides of the connection is the same. With that in mind, we can consider just half of the whole connection. The one you see at the right is simply the side view of the isolated section we considered. From the isolated section, if we will consider the bolts involved or affected by the tensile load T, which causes bolt failure, we can see that there are 4 of the 22 mm diameter bolts used in our connection. And now, we can see where the shear area AV is, which we must consider in solving what is being asked in this question. Take note that the shear area is simply the area where the bolt failure might occur, in which if we will isolate a bolt in the section we are currently considering, the shear area is located at the red lines as shown above. If T acts in such a way that it will cause bolt failure, our isolated bolt would fail like this way. Using now our formula, we now have our FV being the allowable bolt shear stress equals V over. Take note, the AV or the shear area we must consider is not only for one bolt but the total shear area that is at our considered section. From our section, we can clearly see that a shear area is simply the formula for the area of a circle given its diameter, because what is given at our situation is the bolt diameter. Therefore, we will have pi over 4 dB squared multiplied by the number of bolts involved. If you'll pay attention at the side view of the isolated section, we actually have double shear. Hence, we must multiply 2 to complete our expression for the shear area AV. FV is given as 120 equals V over pi over 4 dB being your bolt diameter as 22 squared times 4, which are the number of bolts involved, times 2. Solving now for V, we will get a value approximately equal to 364,927.4 newtons, which is just equal to the value of the allowable tensile load T. Converting that to kilonewtons, it will give a value of approximately 364.93 kilonewtons. And this is the final answer for the third question. Now, for the last question, we are still asked for the allowable tensile load, but based on bearing of the projected area on plate. Therefore, T would cause bearing failure at our connection. Up to this point, the same concept, stress is equal to force over area, will still be used because our formula for this case is this. Stress being the bearing stress, Fp, which at our situation is given as 1.5 Fu. And Fu is also given as 400 megapascals. Force F is your allowable tensile load, which you are solving for this case, and area being the bearing area, AP. To better understand the bearing area, let's consider just half of the whole connection. If T acts and causes bearing failure, the bolts will loosen over time and holes will form in the plate. This is the bearing failure. However, what we need to consider is the fact that the bolts are being pressed at this area, which is the point of contact between the bolts and the plates. And that is the location of the bearing area. To better see the bearing area, let's isolate a single bolt and our critical plate, which is still the middle plate. As the bolt hits the critical plate, it will look something like this. And thus, the bearing area can now be clearly seen. To better view the bearing area, let us consider the side view. This is the part of the bolt hitting the critical plate. Again, this is the bearing area. Having a length of dB or our bolt diameter and a width of T2 or the thickness of the middle plate. Going back, FP is given as 1.5 FU equals F over the bearing area, if you'll notice, is simply the area of a rectangle, which is length times width. Therefore, as mentioned a while ago, our length is dB or the bolt diameter multiplied by the width, which is our thickness T2. Don't forget to multiply the number of bolts involved at our case. FU is given as 400. Hence, we will have 1.5 times 400 equals F over dB is still 22, T2 is still 16, and the number of bolts involved are 4. Solving now for F, we will get a value equal to 844,800 newtons, which is just our allowable tensile load P. And converting this value to kilonewtons would give us a value equal to 844.8 kilonewtons. And this is the final answer for the last question. And here ends our video. Thank you for watching.